Today's lecture is on value at risk and expected shortfall. Let me start by giving you an outline of today's talk. There are two important risk measures that will be introduced today. That's value at risk and expected shortfall. And why are these measures so important? These are measures that are concerned with extreme events that could occur to a financial portfolio. And on top of that, these are measures that summarize the overall risk of a financial institution or of a financial portfolio in a single number. So that's a very efficient way then to look to risk. So value at risk and expected shortfall will be first formally introduced and shown some examples. And then I will briefly move to the concept of coherent risk measures, because risk measures, in order to use them also afterwards to do risk mitigation and risk control, risk measures need to possess certain properties. And what we will see is that expected shortfall possesses all these properties to be a coherent risk measure, and value at risk sometimes does and sometimes does not. So we need to be careful with using value at risk as a measure. Value at risk is a very popular risk measure, and so to a large extent today we will focus on properties of value at risk, and also on, well, if you know value at risk for an individual asset, how do you move to a value at risk at portfolio level? And once you have value at risk at a portfolio level, so then you have an overall assessment of the risk of the entire portfolio, could you then, as a second step, do an attribution of that overall risk to the various assets in that portfolio? So the concept of risk allocation. And I will end today's lecture with briefly discussing how to backtest a value at risk model. The idea behind it is that first you determine what you believe is the adequate assessment of the risk of a portfolio. So you determine a value at risk. Then you can use that to set limits and to control the risk in the portfolio. Then once the value at risk has been determined, of course, then you could look for a while, say for 2 months, 3 months, 4 months, you could observe what the actual losses are in a portfolio. And then the question is, well, are the actual losses that you observe in your portfolio, are they consistent with the risk assessment that you did up front with the value at risk? Well, you would hope that that is the case, because then of course the value at risk gives you a proper risk assessment. If that's not the case, then you need to adjust the way in which you determine the value at risk, and you need to adjust then your investment strategy to stick again within the value at risk measure. First of all, some background. We are again looking to this uncertain future, and because the future is uncertain, we also then will be faced with the risk that a particular value in our portfolio will diminish, will decrease. And what we have done in the previous lectures, we have set up a risk sensitivity system where we have said, well, could we measure the exposure to certain important macro market variables? Those were the risk sensitivity, so the duration and the convexity and the delta and the gamma and so on. And we also have addressed in some extent, well, how could we represent the movement in these underlying market variables? And that's where we have introduced volatility and correlation and so on. So in a way, what we have done is we have built a large system with many risk sensitivities and many factor volatilities and co-movements, etc. And this system has become huge, and it allows us to really assess the risk for many different assets in our portfolio. Now the question that pops up obviously is, well, given that you have this large system, could you, as a second step, also summarize then the overall risk that is there in your portfolio? Can you summarize that in a single number? And a popular way of doing that, so I say the first measure that was put forward to represent the risk in your portfolio, the overall risk in your portfolio, is by the concept of value at risk. VAR, value at risk. And what the value at risk does, it says, well, I will mention a particular loss number, and I'm very certain that that the actual losses will not exceed that level. So the probability that losses will occur that are even more extreme than the value at risk that you will report, that probability is small. So we would say, well, we are very certain, we are X% certain that that will not happen. So there are two dimensions associated with a value at risk. We talk about a time period. So you could mention that, well, you could introduce that by the letter capital T. And we mention a certainty level, X% certain. So we could, for example, say, well, we are 99% certain that in the next year or in the next 10 days, the loss will not exceed a value at risk number that we will define. So I'm very certain there's only a very small probability, a probability of 1%, that it will exceed the value at risk that I state. And of course, that's a neat way of looking at it. So, well, of course, we know that we can never be 100% certain because more extreme events could occur, but we are very certain, at least we are certain with a high probability level that the value at risk will not be exceeded. And we will look a little bit further to these numbers and to the properties of VAR, value at risk, later in the lecture. Value at risk has found many applications. In particular, if you look to how regulators for financial institutions impose restrictions on financial institutions, they have introduced the regulatory capital requirements, and regulatory capital requirements are actually based on a value at risk calculation. So there is, for example, a market risk capital requirements where a bank is supposed to first calculate the value at risk of its market risk portfolio at a 99% certainty level, and then for a time period of 10 days, then a loss number, potential loss number pops up. We say we are 99% certain that in a period of 10 days, the VAR will not be exceeded. There's only a 1% probability that the loss will be even more extreme. And then the market risk so the market risk capital that a bank or another financial institution is imposed to set aside is then a multiple of that VAR number. So you need to multiply that then with a number K, and that K needs to be at least 3. That's the regulation on market risk capital requirements. And then moreover, under Basel II capital requirements, if we look to capital requirements for credit risk, of operational risk, then also the capital requirements again are determined by looking to a value at risk calculation for the portfolio of the bank, for the credit risk sensitive portfolio of the bank, or for the operational risk activities of the bank. So again, a value at risk is calculated now with a horizon of 1 year. So what could happen in a 1 year period? And there we are supposed to give a VAR where we are 99.9% certain that a loss should not exceed the VAR number. So there's only an 0.1% probability that we state a value at risk number and that the loss will be more extreme than that. So very nice, value at risk captures an important aspect of risk in a single number. It looks to the extreme events. It looks very far in the left tail of a return distribution. So how negative could returns get? It's a very simple question that will be answered. So how bad can things go? And it's easy to understand. So it's a very nice variable that has become very popular in the financial industry. There is a second important risk measure that summarizes a risk in a single number, and that's expected shortfall. What expected shortfall does is it says, well, if risk gets really bad, so if there is really huge losses, so if the losses will exceed the value at risk, then, and we know that, then what is then the expected loss that we should think of? So it looks and say further in the tail and takes then a weighted average of the possible losses that could occur if losses exceed the value at risk. It's slightly more difficult to interpret. It's also afterwards when we want to see whether the expected shortfall model works. It's more difficult to backtest the accuracy of such a model. And so those are a little bit the disadvantages of the model, of the expected shortfall risk measure. The advantage of expected shortfall is that it's a coherent risk measure. I will mention in a minute what is exactly meant with a coherent risk measure, but at least for a measure to be a coherent risk measure, it means that all the relevant properties that a risk measure should have to properly use it also in risk management, expected shortfall possesses all these risk measures. So that's important. Then value at risk, while it's easier to understand, easier to interpret, and easier to calculate, so the disadvantage of value at risk is that it's not a coherent risk measure. So at least sometimes one of the requirements to be a coherent risk measure is violated, and that may be a risk if value at risk is used for risk control, because it may mean that traders would abuse this flaw in the value at risk measure to circumvent the risk control and then take very risky positions. Well, for measuring risk, valued risk remains very attractive. So if we want to manage risk, so afterwards impose restrictions to portfolios or to assets to be traded in, it may seem that, say, to fully control the risk, we should not only use valued risk, but we should also include expected shortfall or other considerations, other limits that you could impose to really be certain that risk is properly controlled. So to visualize a little bit what we are talking about, at the bottom of this slide there is a graph. On the x-axis are the possible returns that could realize on a portfolio in a period of 1 year from now. So we see returns as low as -60%, then -40, -20, 0, 20, 40 and 60% that could occur on this portfolio. This is a probability density function, so that's the blue line, and we see that most of the probability mass is in the center, so between 0 and 20%. So these returns are most likely to occur. We also see that there is some significant probability mass between -20% and 0, so also some significant losses could occur. But now the relevant question, so what is really an extreme return that could occur? And there should be only a small probability that the return is even worse. So what I did here, as I said, well, let's say that I want to be 95% certain that I mention in return that where the actual realization will not be worse. So that means that there's only a 5% probability that the return that I mention is worse. So if I look to this graph, then the value at risk is -22%, and that means that I expect in a period of 1 year from now that there's only a 5% probability that the return that will realize is even worse than the -22%. So the value at risk that I quote say, well, this is a significant negative return, minus 22%, only 5% probability that it will be even worse. So that's a nice feature. That's summarizing very nicely risk in a single number. Then the second thing that you could do with this graph is you could say, well, if returns really become very bad, so that means if they are minus 22% or lower, and then so the blue line shows that there's possible returns between minus 22% and say minus 60%, then what I'm going to do to determine the expected shortfall, I'm going to consider all these returns, minus 60%, minus 59, minus 58, and so on until minus 22%. These are all possible returns that could occur if things really go bad. So that's all returns worse than the value at risk. And these returns, I'm going to take the average of them, but I'm going to take a weighted average. And what I use as a weight is, in fact, the probability mass that's provided by the probability density function, so the blue line. And because I only weight the returns below the value at risk, I normalize these weights by dividing by the probability mass in that tail. So I divide them by 5% after I've weighted, and then the weights actually are 1%. So in a nutshell, two risk measures, the value at risk minus 22%, which says, well, I take a threshold and I'm 95% certain that this threshold will not be violated. So it's only 5% probability that returns will be worse than minus 22%. And then the expected shortfall, I look to all the possible returns which are worse than the value at risk, and I take a weighted average of them. And in this case, the weighted average turns out to be minus 29%. Then next, a coherent risk measure. When do we call a risk measure coherent? Well, coherent risk measures are important because they have some desirable properties, and if I mention them in a minute, then you also will say, well, hey, that makes sense that risk measures possess these properties. And then if they don't possess these properties, it means that very often that some inconvenient trading could occur where the risk is violated. So the first property is monotonicity. And what that means is, well, if I look to two variables, and if one variable always has a better result in every state of the world than the other variable, then this variable that always is better in every state of the world, it should have a lower risk. It makes sense. Then the second measure, which is what we call translation invariance, is if I have a particular portfolio and I add cash to that portfolio, cash is risk-free, so you cannot lose anything on cash, then the risk should go down consistent with that amount of cash that I added. Makes sense. Then homogeneity. If I have a particular portfolio with investments and that portfolio has a certain amount of risk, if I double that portfolio, then also the risk of the portfolio doubles. And then the fourth one, which is a diversification measure, it says, well, if I look to two risk measures and they have both a certain amount of risk, then if I take the sum of these two risk measures, or I take the sum of these two variables, or I take the sum of these two investments, then the risk of that sum should be lower than the sum of the individual risks. And it's this last requirement, so that's diversification requirement, it's this last requirement that sometimes may be violated in very special cases by the value at risk. And that's why we say, well, expected shortfall probably is a preferred risk measure, because it always meets these four requirements of a coherent risk measure, and value at risk may violate the sub-additivity requirement. I also have to mention that in practical cases, the portfolios that I look like with very plain vanilla investments, I do see that the value at risk measure does not violate this sub-additivity requirement, but that's not to say that it's not sometimes the case. So it's something to be taken care of. Then there are a couple of attention points that I want to address before moving forward. What you have seen when I showed you the graph is I showed you the graph of a probability distribution function for a return. And what I like to do when I talk about value at risk is simply to talk about the return distribution. And when I talk about a loss, then a loss for me goes hand in hand with a negative return. So a loss actually is an amount that you lose, which is a positive number, and it's a positive monetary value. It's, for example, $1 million that you could lose. So I don't do that. So I only look to one type of measure, unless stated otherwise in the lectures. I only look to the return distribution, and whenever I talk about a value at risk, it's a negative return that will arise, just like in the example. And the reason why I do that is because, well, a lot of the theory that will be mentioned is determined or is driven by probability distribution functions. And because I only look to returns, I only am concerned with the return probability distribution function. And otherwise, there is sometimes the risk that it's uncertain whether I talk about the return distribution function or the loss distribution function, whether I talk about the monetary value or whether I talk about the percentage value. So unless stated otherwise, whenever I talk about value at risk and expected shortfall, I always talk about returns. That means that both expected shortfall and value at risk are very simply negative return numbers that will be represented. So for value at risk, it's the threshold of a negative return as a negative return. For expected shortfall, it's the weighted average of negative returns, but in the end, it's both a single number and it's both a negative return. And then the reason why that for me is an easy way of doing it is that, say, if afterwards you actually want to know, well, what is then the amount that I could lose? So that's formally what the value at risk wants to express. Then you simply apply that negative return to the value of your portfolio, and then you know what the loss is. So it's simply one step before I actually go to the final number that I want to express. But then it stays at least very clean. We only talk about returns, unless stated otherwise. Then a second attention point, and this has to do with inconsistency between the usage of different conventions. When we talk about tail probabilities, then we talk about, well, there should only be, we should be far in the tail of a distribution function, which means, well, we are looking to returns that are unlikely to occur. So we are far in the tail. So there's only a 1% probability or a 5% probability that these returns could occur. Alternatively, you could also talk about certainty levels. I'm 99% certain, or I'm 95% certain. Well, what is important whenever you see a probability that is expressed, because sometimes people use the 99% and sometimes people use the 1%, what is important is that you always certify for yourself what kind of number that we are talking about. And really what you want to verify is that when we talk about the tail, it should be the low probability that we talk about, whatever it's mentioned. So what you will see, and that's a slight difference between the book and how I would like to use probabilities, is where I in my slides use X very often for the probability in the tail. So then that X you should think of, that's, for example, a 1% probability. In the book, often then with the X, they refer to the certainty level. So they refer to the 99% level. So if you read different articles or you read different books, these probabilities are used one after the other, so it's not very consistent. That's why the formulas that you may see on the slides sometimes also will deviate slightly from the book. But remember, whenever you see the probability or you see the certainty level, it should be such that when we talk about the tail, you have the low probability, and then everything should be fine. It's anyhow something that you should always verify when you read an article. Well, what is it actually that they refer to when they talk about the probability level? Let's start with a very simple example. And for this example, I assume that, well, we look to a single asset to begin with. And I assume that this asset has a return which is normally distributed with a mean of 10% and a standard deviation of 15%. So that's a representation of the uncertainty of the return over a period of 1 year into the future. I assume normal distribution function. To determine a value at risk, that comes in very handy to make this probability assumption of the normal distribution function. And throughout the chapter, we will extensively make use of that normal distribution function. However, it's not necessary for a return to be normally distributed to determine the value at risk. I could determine the value at risk for any type of distribution function. What's relevant for the value at risk is that I look in the tail of the distribution function, whatever the distribution function is. But in this case, we use the normal distribution function. So the question now is, well, what is the value at risk, both at a 5% level and at a 1% confidence level? So again here, think about the conventions as I just mentioned. So 5% and 1% confidence to me means that the tail has 5% probability mass or 1% probability mass. So other people may have expressed this as 95% confidence level or 99% confidence level, but just it should be clear from the context here that the 5% confidence level refers to the left tail. So how do I determine the value at risk? So I need to know what the percentile is or the quantile is at the 5%. Well, with normal distribution functions, what you always do is that you first go to the critical values that are determined for a standard normal distribution function, and then you use them to apply them to non-standard normal distribution functions. So a standard normal distribution function goes with a variable z, which is usually denoted with z, which has a mean of 0 and a standard deviation of 1. So the critical value, the percentile for a standard normally distributed variable at a 5% confidence level, so that means there's only 5% probability mass in the tail, is determined by taking the inverse of the standard normal distribution function at 5%, and that's a number that you could look up in a table, or you could use, for example, Excel to determine that. In Excel, that would be norms inverse to determine it. And that critical value for the standard normal distribution function is minus 1.645. So what that means is that, well, this z is standard normally distributed, normal 0, 1. It means that the probability of this random variable z to drop below this critical value of small z 5% is 5%. So the critical value of a standard normal distribution function at the 5% level is minus 1.645. A similar story applies, well, if I have only 1% probability mass in the tail, then what's then the critical value for a standard normal distribution function? It's minus 2.326. And then these numbers that you will have to look up very frequently if you're going to do value at risk calculations, These numbers will then subsequently be applied for non-standard normal distribution functions, because here I talk about a return with a mean of 10% and a standard deviation of 15%. So then the value at risk at the 5% level for this asset return is the mean of 10% minus the critical value that I have determined from the standard normal distribution function, minus 1.645, times the standard deviation of the asset return of 15%. So which means that I arrive at a value at risk at the 5% level of minus 14.6. So how to interpret this number? There's only 5% probability that in 1 year from now a return will realize that's worse than the minus 14.6. So suppose I want to be more confident, more certain. Suppose that I want to know the value at risk at a 1% level. Again, what I do, I take the mean of the asset return of 10% and I add to that the critical value of the standard normal distribution function, but now at 1%, minus 2.326, times the standard deviation of the asset return of 15%, which gives a return of minus 24.9%. So how to interpret the minus 24.9%? There's only a 1% probability that in 1 year from now a return will arise that's worse than minus 24.9%. So then the minus 14.6 and minus 24.9 gives you reasonable ideas of what is it that you should think of if you think about risk in 1 year from now. And you should be quite certain and that these numbers apply. I mentioned already, very often we use a value at risk in the context of a normal distribution function. Not necessary, one more time, but if we do that, then then some notation. The return is normally distributed with the mean of mu and a variance of sigma square. And then if you look to the formula that I just applied in the example on the previous slide, that formula is actually that I take the value at risk at a certainty level of x, which is the mean of that return plus the sigma of the return times a critical value times the norms inverse evaluated in x. X again is the probability in the tail, so it's the low number, it's the 1% or the 5%, and this inverse of the cumulative standard normal distribution function, that's again the number that you look up. So this is the relationship that you then would apply. Very often what you see, in particular if you look to trading books, then the horizon to determine a value at risk is small. It's 1 day or 3 days, 5 days, maybe 10 days, maximum 20 days. Then in that case, the volatility is much higher than the mean of the return. And very often the mean of the return has very little to none impact on the risk because it's so small. So very often, to simplify then the formulas, the mean is set equal to 0. And then what we have is we see that the value at risk is really a proportional number to the volatility of the distribution function. So if the volatility of the distribution function, the standard deviation, is higher, then also the value at risk is higher. So we simply multiply the standard deviation of the distribution function with a critical value from the standard normal distribution function. So that's the minus 1.645 at the 5% level, as we saw in the example in the previous slide, or the minus 2.33 at the 1% confidence level, also that we saw in the previous slide. And that's also, so once more, why you see why volatility is such an important measure to handle with. Then, if we are in the context of normal distribution functions, and but we also look to not a one period model horizon, but to multiple periods, then we know that the uncertain future is represented by multiple returns. And what we can do if we want to know the price of an asset at time capital T, we simply take the price of that asset today at time 0, and then we multiply it with the exponent of the sum of all the 1 period, 1 year, for example, or 1 day returns. So you could simply add up these returns, and then the sum of these returns, so that's the sum from t is 1 to capital T, so it could be, for example, the sum of all the returns in the next 10 days, then this return also is normally distributed. So I denote that return with a capital R evaluated at time capital T, so a longer period. It's the same as all the 1 period returns, the small RTs that I add up. And then it's very easy to show that if each return is normally distributed with a mean of mu and a variance of sigma square, that the sum of these returns, they have then a mean of mu times capital T times the length of the period, and the variance of that return is sigma square also times capital T. So the standard deviation of this longer term return is sigma times the square root of capital T. Now, if I want to determine not the 1 day value at risk, but for example the 10-day value at risk, then capital T is 10. Then the formula that applies is that, again, you take the mean of the return, which now is mu times capital T. You take the standard deviation of the return, which is sigma times square root of capital T, and you multiply that with the critical value of the standard normal distribution function times the norms inverse at x. Then the question is, well, if I have determined the value at risk at a 1 day level, at a 1 day horizon, can I then also use it to determine the value at risk at a multi-period level under the assumption that these returns all remain the same? And the answer is yes, because the value at risk at a 1 day level is simply mu minus sigma times the inverse of this standard normal distribution function. For time capital T, the variance is the mu times capital T minus, and here's a sigma missing in the formula, sigma times square root T times the variance of the other one. And what I will do, sorry, let me go back. So the variance of at a longer horizon time capital T, what I will do is I will substitute for the variance of the 1 day, I will take sigma times the norms inverse that you see on the top. That's equal to the variance at 1 day level minus mu, and this is what I substitute in the multi-period value at risk. And then what arises is a relationship between the value at risk at a longer horizon time t, say as a function of the value at risk at a 1 day level on the right hand side. Well, let's see how that works. Again, see, what I will do is, if we look to short horizons, I will assume in the next example that the mean is equal to 0. And then simply what arises is a relationship between the 1 day value at risk and the multi-day value at risk, and it's simply a square root formula that arises there. So what I need to do, if I go from 1 day value at risk to say, for example, 16 days value at risk at the same critical value, then I simply need to multiply the value at risk that I've determined at 1 day with the square root of time. So if I want to extrapolate to a 16 days value at risk, I take the square root of 16, which is 4, which then really says as well, if I know the value at risk at a 1 day horizon, then if I multiply it with 4, then I have the value at risk at a 16 day horizon. So that's the value at risk in the time horizon, how that applies. Then, if we want to look to the value at risk and confidence levels, suppose that I have, well, again, I use the normal distribution function, Suppose that I've determined the value at risk at a particular confidence level, say at 5%, and I want to go to a different confidence level, say 1%, then of course I could do the calculation separately again at the different confidence level. But again, also here there is a relationship between the value at risk at one confidence level and the value at risk at another confidence level. And that relationship is summarized in this formula. So x prime or x star is the higher confidence level, so is for example the 1%, and the x, it's the lower confidence level, it's x. And then the question is, well, if I have already determined the value at risk at the x% confidence level, so that's the value at risk Tx on the right hand side, how can I then determine the value at risk at the higher confidence level, at the 1%, for example? That's x prime. And what you need to do is you really need to know the critical values from the standard normal distribution function, which you then first determine at the most certain level, at the x prime level, but you also look to the critical value of the standard normal distribution function at the original level at x. So you take the fraction of the two, and then you multiply the original value at risk that you have determined at the x level with that number. So there's also expected returns, say, arising here. So those are the mu's. But again, if we look to very small time intervals, then these mu's are almost equal to 0. So you could simply then take them out. You could leave them out. They have no effect. And then you see that the value at risk at a higher confidence level or at a different confidence level is simply a multiple of the value at risk at a lower confidence level, where the relationship between the two is fully determined by the critical values of the standard normal distribution function. So let's look back to the example that we had before. So we had the critical values of minus 1.645 at the 5% level and minus 2.33 at the 1% level. So if I do the minus 2.33 divided by the minus 1.645, and I multiply that in this case with the difference between the original value at risk of minus 14.6 minus the mu, and I also add up the mu, then I arrive at a value at risk of minus 24.9. And this was exactly also the value at risk that we in an early example had calculated individually separately for the 1% level. But here, instead of do the calculation separately, we make use of that 5% value at risk calculation and simply multiply it with the fraction of these two confidence levels. So we have discussed the value at risk and its properties. So next what we will do is we will go one step further and we will go and look to the expected shortfall. Expected shortfall is to a large extent related to the value at risk. So let's introduce again notation. I assume again that we look to the value at risk for a return, and that return is normally distributed with a mean mu and a variance of sigma square. And we know that the value at risk then follows as the mu plus the sigma times that critical value again of the standard normal distribution function in the tail. So x is again the probability in the tail, is the 5% or the 1%. Then once I know the value at risk, I could then next determine the expected shortfall that is associated with this value at risk. And again, what you do is you say, well, I'm going to look to all the returns that are worse than the value at risk. And I'm going to take an average of that, a weighted average. So the formula here shows an integral from minus infinity to the value at risk. So it says, well, look to all the returns between minus infinity and the value at risk return. That's many different returns. And this return is denoted with y. And I'm going to add up these returns, but because returns are continuously distributed, the integral should be read as a sum in continuous time. So I'm summing up all the y's, but I weigh them with the gy, and I divide them by x. So what is the gy? The gy is the probability density function of the return. So I'm going to look to the normal distribution function and its density, so which is 1 over 2 pi sigma times the exponent of -1/2 y minus mu sigma squared. That's the probability density function of a normal distribution function. So that's going to be used as a weight for each negative return that could occur between -infinity and the value at risk. What is important to know is that that critical value, the probability in the tail, the 5% or the 1%, it's exactly the sum of all the probability mass of that probability density function. So if I look from -infinity return to the value at risk as a return, and I look to all the probabilities that come with it, and I add them up, then I exactly arrive at x, so at the 1% or at the 5%, so at that critical value. So then the expected shortfall indeed is a weighted average of all the returns that are worse than the value at risk, because I look to the range of -infinity to the value at risk, x, so that means all the returns in that region. The y are the returns, and then if you look to the formula again, you see it's gy divided by x, but this x was exactly the integral of gy dy. So then you could say that the weight of each y that you use in the formula is simply the gy divided by the integral of -infinity over until the variance of x of gy dy. So that's exactly a number that if I would also take the integral over these weights, then I exactly say add up to 1. So then these are proper weights. So the expected shortfall is a weighted average of all the returns lower than the value at risk. That's what the range is. And the weights are determined by the probability density function of the normal distribution function of the return, and it's normalized by dividing by the probability mass in the tail, so that these weights actually add up to 1. Let's see next if we could have a more usable formula for that integral. So if you're going to solve that integral, then the expected shortfall where the critical, where the probability mass in the tail is denoted with x, could be written as the mean of the return distribution, the mu, minus the sigma of the return distribution divided by the critical value, the 1% or the 5%. And then you multiply that with a probability density function f, which is the probability density function of the standard normal distribution function. And I've mentioned that below, so then it has a mean 0 and a standard deviation 1. And then you evaluate that standard probability density function of the normal distribution function in the value at risk number minus the mean over the standard deviation. So you could rewrite this expression simply in an expected shortfall, which is then equal to the mean of the return minus the standard deviation of the return divided by the critical value, the probability mass in the tail, and then evaluating the standard normal distribution function in the cumulative normal distribution function inverted in the critical value. So in fact, look to the standard normal distribution function and look what the critical value is with a probability of x. So this norms inverse x, for example, it was minus 1.645 when x was 5%, and it was minus 2.33 when x was 1%. And that's the number that you fill in the standard normal distribution function in f. So I've expressed it a little bit different at the bottom. So there you see substituted the standard normal distribution function. So now the 1 over 2 pi exponent of minus and half y squared is incorporated. So that's a description of the standard normal distribution function, and then the y is then the critical value, the minus 1.645 of the minus 2.33 that come from the standard normal distribution functions. So these are nice formulas that could be applied. So to give you an idea, if you actually are going to calculate the value at risk and the expected shortfall with a normal distribution function, I used the formulas on the previous slides to determine the value at risk and the expected shortfall in the case of a return that has a mean of 8% and a standard deviation of 18%, and I took different probability mass in the tail, and then every time calculated the value at risk and the expected shortfall. The first case that I considered was a probability mass of 25% in the tail. That's not really a very low probability, but it's there more merely for illustration purposes. So then the value at risk is minus 4%, and there is a 25% probability that in 1 year from now the return will be even worse than minus 4%. And then if I also determine the expected shortfall, then I'm going to look to all the possible returns lower than minus 4%, and I'm going to probability weight them with a probability density function of the return. Then the expected shortfall is minus 15%. Then the critical value, so the probability mass that I allow in the tail, 15%. Then it says, well, there's only a 15% probability that the return in 1 year from now will be worse than minus 11%. And then we also determine the expected shortfall with that. So we look to all the possible returns between minus infinity and minus 11%. And we weigh them again using the probability distribution function. And we arrive at minus 20%. And so on. And then let's look to the more interesting cases. We see at 5% the value at risk becomes minus 22% and the expected shortfall minus 29%. At 1% minus 34% and minus 40% respectively. And if you go further in the tail, so if you go as far as a probability of 0.01%, so that's a very low probability of occurring, we see that the value at risk is minus 59%. So there is only a probability of 0.01% that the return in 1 year from now will be worse than minus 59%. But if I look to the weighted average of the returns between minus infinity and minus 59%, then the expected shortfall in that case would be minus 63%. So again, I'm not talking about losses, whereas value at risk and expected shortfall should be talking about losses. Losses are positive numbers with, which are often expressed in monetary values, in dollars or in euros. So I leave it here, so I leave it with negative returns. It's very easy afterwards to move to the actual monetary loss, because you look to the initial value. And if then, for example, the value at risk is minus 15%, then you do 15% of the original value, and that is then the amount that you are stand to lose. So far, we have to a large extent been talking about a value at risk calculation on individual assets. Now we move one step further, and what I did is I constructed a very simple a portfolio of 4 assets, which is very easy to generalize to larger portfolios. And to simplify things with these 4 assets, I said, well, let's assume that they are jointly normal distributed, that I know the expected returns, that I know their standard deviations, the volatilities, and I know to what extent they correlate. The total portfolio value is 10,000, and we see that asset 1 has a value of 1,000, asset 2 has a value of 2,000, asset 3 3,000, and asset 4 has a value of 4,000. That means that they have different weights in the portfolio. So you look to the value that they have divided by the total value. So that's 10, 20, 30, and 40% for asset 1, 2, 3, 4 respectively. You see that their means are different, 4, 5, 6, and 8%. And you see that their standard deviations are different, 12%, 13%, 50%, and 18%. They also co-move, and the co-move is reflected here with linear dependence. So I show the correlation that are there. Then I use a little algebra to also determine, well, what is then the expected return on a portfolio level. And well, as we will see in a later chapter, you very simply then take the weighted average of the individual expected returns. So in this case, if I do that, I need to multiply the weights with the mu's and then add them up. And then on a portfolio level, the expected return is 6.4. And to determine the standard deviation on a portfolio level, you need to take all the possible combinations of the correlation times the individual standard deviations times the individual weights. You add them all up, and then you take the square root of that, and then, at least in this example, the standard deviation on portfolio level is 12.92. So that's nice, because if I want to determine the value at risk at portfolio level, I can now move back to the formula, and we assume normal distributions. I can move back to the original formula that we had for the value at risk, and knowing the mean and the standard deviation, I simply need to take the critical value from the standard normal distribution function, and where before I applied this formula to individual assets, now I will apply it to the return on the portfolio level, because I now know the mean and the standard deviation on portfolio level. So if the critical value is 5% for the value at risk calculation, I do as I did before. I determine the value at risk at 5% level by taking the mean of that portfolio return. I take plus the standard deviation of the portfolio return, and I multiply that with the critical value of the standard normal distribution function at the 5% level, because that's the probability mass that I still allow in the tail. That's minus 1.645. If I do that calculation, I arrive at a value of minus 14.85%. The portfolio original had a value of 10,000. So that means that the monetary amount that I could lose then is 14.85 times percent times this 10,000. So that's $1,485. So what I want to do next is I also want to do the same exercise first on each asset individually, because I could determine very simply the value at risk for each asset in the portfolio, because I know its mean, I know its standard deviation, and I know the critical value, which is minus 1.645. So if I do that, so if I do the calculation of each asset individual, I get for asset 1 minus 16%, asset 2 minus 16%, asset 3 minus 19%, asset 4 minus 22%. And then if again I look to the monetary value that I'm standing to lose if I would apply this value at risk on the individual assets, it's minus 16% on the 1,000 value for asset 1. Well, because the 16% was rounded, you don't see it, but then the amount that you stand to lose is $157, and for the second one is $328, then $560 and $864. So that's assuming that I look to all the value at risks individually. I don't look to them in a portfolio context. If I would add them up, these individual losses, I arrive at a potential loss of 1,910. And so here you see an important difference between first looking first considering, well, what is the return on a portfolio level, and simply applying the value at risk to each asset in the portfolio individually, and then see what all the losses are and add them up. So we see that at a portfolio level, the 1,485, that's a lower number than the 1,910. And the reason for that is that, say, in the second application, where we apply the value at risks on all the assets individually, we do not take account of the diversification benefits that you may have if an asset is part of a portfolio. So the co-movements are not perfect, which is reflected by the correlation matrix, which means that there's a lower risk because of assets not perfectly moving in tandem. So the difference is quite substantial if you look here. So it's not correct if you want to do a value at risk assessment on a portfolio level. So you should not determine then the value at risk on an individual level and then add them up. Instead, you should first look what the distribution function is at the portfolio level and apply those parameters then to determine the value at risk. So the example here shows that. Now the second question that pops up is, well, if I have determined the value at risk at a portfolio level, could I then also assess what the contribution is of each asset, each individual asset to that value at risk at a portfolio level? And the answer is yes. And so what we do to determine that is we introduce the component value at risk, which is in this case denoted with the C var, and the subscript I is that we then determine it for asset I. So what the formula suggests is that we can determine the component vars for each asset, and then if we add them up, then we exactly arrive at the value at risk that we determine at portfolio level. And then, as we know from Euler's theorem, we know how to determine that. This component var is simply the partial derivative of the portfolio var if there is a small change in the value in the investment of asset I, multiply with the value of asset I. And I've rewritten that slightly, so I have brought the xi into the denominator, because then there is a nice interpretation. It says, well, what you need to do in the denominator, it says, well, just change the asset value with a very small fraction. And then in the numerator, you look, well, if you do that, then how does the value at risk at portfolio level change? And then if I divide this change in that portfolio level by that very small change, then I know what the component for value at risk is. And so once more, what am I going to do? For each asset separately, so I start with asset 1, I'm going to, well, I had already calculated the value at risk at portfolio level, so that number stands. But I'm going to do another calculation of the value at risk at portfolio level. And what I do is I do one very slight change. So, for example, for asset 1 to begin with, I'm going to change the value that it has in the portfolio with a very small number. So what I do is, well, it had a value of 1,000, but I'm now going to change that value in 1,000 times 1.0001. So there is a little bit of an increase in the value of that portfolio. When that portfolio value changes, then if I do all the calculations, I also arrive at a slightly different value for the value at risk at portfolio level. So you use the same say formula as before, but the number that comes out is slightly different. Then I'm going to look at what is the difference between the value at risk at portfolio level after I made this small change, and what is the difference with the original value at risk at portfolio level before I made that change. And that difference I divided by the very small number, by the 0.0001. So by the little shock that I've given. And then the number that arises, for asset 1 in this case, is then the component var for that first asset. Then I'm back to the original case, and now for asset 2 I'm going to do something very similar. So I had already calculated the value at risk at portfolio level when all the asset values are as they are originally in the portfolio. I'm going to shock only one value of the asset. So I'm now going to look to asset number 2. I'm going to multiply its value with 1.0001. So it's going to be a slightly higher value for asset 2 now. Well, when that's the case, and I'm going to calculate the value at risk at portfolio level again, I also will arrive at a slightly different value for the value at risk at portfolio level. So I determine the difference with the original value at risk at portfolio level, and that difference again I divide by 0.0001, and so on. I do that for all the assets. So let's see if I do that, what happens. Then for asset 1, which had a value of 1000, you see that the value at risk of the component var that I've calculated then will be 59. For asset 2 it will be 271, asset 3 386, and for asset 4 770. So if I add these numbers up, then indeed I arrive at 1485, and that's exactly the dollar amount that we calculated originally when we determined the value at risk at portfolio level. So we do see here that indeed it's possible to determine the value at risk at portfolio level and then to attribute, to allocate the contribution of each asset to that value at risk in dollar amounts. So how should you interpret these numbers? Well, these numbers at least suggest that asset number 4 has the highest contribution to the value at risk. So there is 770 that it contributes to a total value at risk of 1485. And the sources of this contribution are many. So it has to do with the asset size of asset 4. It also has to do with the expected return, with the volatility of 18%, which is high. It also has to do with the extent to which it co-moves with the other assets in the portfolio. So it's a summary of all the different elements that contribute to the total value at risk at portfolio level. So this component var, value at risk, it's quite important number that also is used in practice, because it's in the end it's a relevant number when we're going to do risk budgeting. And what we mean by risk budgeting is that we say, well, if we have an institution with many different departments or many different type of activities, then it's important to know, well, if I look to the overall risk of that financial institution, well, where does the risk come from? So what's exactly the contribution of each department or of each activity to that total value at risk? Because once I know that, then I also could say, well, yeah, at least if there is a department or there is an activity that contributes a lot to the overall risk, then I would also hope that the profit that I have from such a department or activity is in sync with that amount of risk. So if I have departments or activities where the contribution to the value at risk is very high, but then the expected profit is not so high, then you would say, well, that's then a relatively unattractive activity or department that I have. So this is now say summarize in a few words how it's used in practice. We will revisit this little bit later in the course, when we're going to talk about how the value at risk actually is used for capital allocation purposes within a financial institution, and also how then the required return on capital is determined for each business unit, each department within a financial institution. So let's move to the last part of today's lecture, which has to do with backtesting of a value at risk. once you have set a value, once you have determined a value at risk and you have set it, and you believe that that's the proper risk assessment, and you also then determine all sorts of risk limits based on this value at risk, then once you start to move to the situation where you're going to use the value at risk in the holdout period, then it's important to monitor whether the value at risk actually is accurate. So that type of monitoring means that I'm going to look to a holdout sample. For example, I'm going to look to 100 days, and I'm going to look to the value at risk, which says, well, hey, this is a particular threshold of loss, and there's only a low probability that you will violate this threshold. Then actually I'm going to look, well, how often actually there were losses, realized losses in, for example, the next 100 days that were worse than the value at risk. Because if there are many losses, then you would say, well, hey, that's strange because my value at risk was set in such a way that it should not happen too often. But if there are many losses, then that's inconvenient because then my model is not sufficiently accurate in assessing the risk, and it's not a proper way then to use the value at risk for risk management, for setting limits and so on. So I gave you an example. Suppose that the critical value was set at 5%. So then the expected number of violations is 5. So suppose that actually you see in the 100 days after the model was set in place, we see 25 actual losses, and you say, well, hey, the expected number is 5. I see 25. That seems a lot compared to what I expected. Alternatively, it could also be the case that your model is too prudent. Suppose that, again, you set the critical value at 5% for your value at risk, and then in 1,000 days there's never a violation, then it seems that your model is too careful. That, of course, is less an issue than when your model is not sufficiently careful, but being too careful in a business environment also means, well, not being taking sufficient risk, not doing sufficient activities that could have added value. So it's not necessarily also something simply not to look at. Now the question is, well, so how should I then form a proper back test to see whether my value at risk model is appropriate or not? So what I will do is I will count the actual cases that there are an actual loss that is higher than the value at risk. So we are talking here now about monetary values, and so the loss is higher than the value at risk, and we count how often. Well, if we had set the confidence level at X%, 95% certain that you don't violate the value at risk, or the probability in the tail is 5%, denoted with P here, then you say, well, at each moment in time, I expect the violation to be 5%. So if I observe small n days, 100 days, then the question is, well, now in these 100 days, if I would see 7 violations, is this value at risk model then appropriate or not? Given that there is statistical uncertainty, it's not like with a probability of 5%, I would say, well, I expect exactly 5% of the 100 days, which is 5 observations, to be violated. No, there is still a statistical chance that 7 is still correct. The probability of M violations, if that critical value of the value at risk, so that small p, which is 5% here, is correct, that is actually a binomial distribution function. So I look to a stochastic variable capital M, which if it has 7 observations, then these 7 observations could be any combination of 7 violations in these 100 days. So that's n boven m times the p to the power m, 1 minus p to the power and that should be n minus m. Then if I do the calculation of this probability of number of violations, and that's what I did on the right hand side, then we see that say with a probability of 0 violations that could only occur in 0.6%, with a probability of 0.6%, 1 violation only with a probability of 3.1%, 2 violations with a probability of 8.1%, and so on. So the colors are slightly suggestive, so where you see that the chances are, the probabilities are the highest, so you say, well, that's quite likely that this could occur. And we see with the very high violations, so if you have 10 or 11 or 12 violations, you see that the probability of that occurring are relatively low, 1.7%, 0.7%, 0.3%. And in fact, if I go further than 13, then the probability mass is so low that I could even ignore it. So that's almost not possible to occur. So what does the formal backtest then pertain? I need to have an alternative for the null hypothesis. And so what we say here is, well, we look to the cumulative probability of number of violations. And if that cumulative normal probability of violations is sufficiently high, then we believe that the backtest still is okay. So we're going to look to the sum of the violation, the probability of violation for the number itself, and for everything higher than that. And if that's higher than my critical value, it's okay. So the 5% is then your critical value. So backtesting occurs at least on an annual basis within financial institutions, or say if there are significant changes in market circumstances, then it happens more often. That concludes the session of today. Thank you for your attention.